In 1960, Freeman Dyson suggested a method for a highly advanced civilization to collect a large portion of a star's emitted solar energy. Often this concept is somewhat erroneously called a Dyson Sphere, as in a solid encasing shell around a star, which Dyson didn't think was possible, but used it as a thought experiment. But the idea is much older, going back to the 1937 novel Star Maker by Olaf Stapledon. The idea as Dyson saw it was covered in his paper, Search for Artificial Stellar Sources of Infrared Radiation, link in the description below, and came on the heels of the beginnings of SETI, as laid out by Cocconi and Morrison. He felt such searches should be done concurrently with SETI, but only a few have, more on that in a minute. Anyone creating such a shell or similar structure would also have the entire interior of the shell in which to host a civilization, far more area than a planet has. A planet can only harvest so much energy and absorbs only a tiny fraction of what its parent star's total output is, so you can only put so many solar energy collectors on a planet's surface, and the planet itself can only generate so much energy. So the idea is that as a civilization advances, its energy needs grow. So eventually they need to harvest more of their star's energy and must do it with space-based collectors. More realistically, it would not likely be an outright shell, but in a large array of individual collectors or a Dyson swarm. But you never escape thermodynamics, so such structures would absorb the sunlight, but also emit it just as brightly in far infrared. That infrared excess would be visible and not normal for a star system if you saw it. One reason for it being abnormal would be the presence of heavy elements not normally visible in a star. To date, there have been several searches, and the strange thing is, most of them yielded candidates. One of the first was in 2006 using the IRAS data. Richard Carrigan at Fermilab looked at 250,000 stars and found that Dyson Sphere candidates were rare but existed. Ultimately, 17 candidates were found, with 4 being particularly interesting. However, all were deemed ambiguous. This was partly because the survey was looking only for blackbody spectra at certain temperature ranges. Another Dyson Sphere candidate was the infamous KIC 8462852, or Tabby Star, that showed a bizarre light curve in the Kepler data that fit that of a partial Dyson Sphere, but only if it were opaque, which was an open question at the time. Measurements have since shown that it was not opaque and did not absorb all wavelengths completely, meaning that it appears to be a phenomenon of some kind of dust, though it's unclear to this day what's really going on in that star system. Oddly, the search for Dyson spheres or swarms is turning out to actually be a very fruitful area of SETI, because these searches keep coming up with candidates. And now we have 2 new searches, and the plot has most definitely thickened. 2 new surveys are out, done with modern equipment, and the catalog of candidates has dramatically increased. The first search was led by Matthias Suazo, and the other, Gabriella Contardo and colleagues, using the Gaia spacecraft dataset among other instruments. Links to both papers in the description below. Both groups studied the same 5 million star overall dataset, and lo and behold, they both produced excess infrared emissions that can't be explained by known natural processes. They appear as what you would expect from Dyson Spheres. In the Suazo paper, they detailed that in their search, they found 7 red dwarfs, all within 900 light-years of Earth, that had a very strange feature. Red dwarfs are smaller, dimmer, and cooler stars than the Sun, and in fact are the smallest type of actual star before getting into brown dwarfs. With these 7 stars, however, they appeared as much as 60 times brighter in infrared than what they should be producing, based on what they're emitting in visible light. That's a lot. And it's exactly what you would expect from the signature of a Dyson swarm, where some of the light is making it past the collectors, but the collectors are emitting in infrared. The temperature of whatever is there would be about 400 degrees Celsius, exactly what you would expect from a radiating Dyson structure. It also requires as much as 16% of the star's visible light to be blocked to account for that much of a difference between infrared and visible emissions. The second paper covered larger stars, including many similar to the Sun. The group of stars included more distant stars, up to 6,500 light-years away, and nearly 5 million of them. all Type K orange dwarfs, Type G stars like the Sun, and Type F stars like Tabby Star. This study found a whopping 53 candidates. It pays to remember, of course, that these are only candidates, and only further observation is going to yield some answers. And it has to be said that there is always a chance that there is some natural way for these stars to give off unusual emissions in infrared that no one has thought of yet. Interestingly, one thing that we know that could mimic this are types of circumstellar disks of dust. But those tend to be a matter of young stars, and none of these candidates, and indeed Tabby Star, are young. They're actually mature stars that should no longer have debris disks unless there was some sort of recent collision of material in the system. But with Tabby Star, it showed no infrared excess at all. It may have been below the threshold of the detector, but recent observations were done by the James Webb Space Telescope in infrared, but the results are not out yet. If it sees nothing, it would send that star into weird territory again, because it would mean that whatever the material is, it's cold. The current models of that star system are based on collisions, which the data on the dips seems to suggest. Then it likely would involve cold comets, as was proposed in the original Boyajian and colleagues' paper. Trouble is, another researcher found that it would require an implausibly high number of colliding comets, in the hundreds of thousands at once, to be in the system to account for it. That star still doesn't make sense. Another unsolved mystery that raises an eyebrow about Tabby Star is that there were a number of other candidates found that are showing this sort of behavior. Work done by Edward Schmidt found 21 candidates for Tabby Star type behavior that, like Tabby Star, show no apparent periodicity and also have wild variations in the depth of the dips. All of the 21 candidates are clustered in two ways. The first is that all of the stars were very similar to Tabby Star in type, meaning that there may be something we don't know about how these stars themselves behave. But if it were the stars themselves doing it, say with giant sunspots, it would go against the measurements done for Tabby Star because they indicated submicron dust very clearly. To date, these stars have not been looked at to determine if dust is at fault. The second is much stranger and takes us into weird territory indeed. The candidates were found to have an overdensity, meaning that they cluster in the same general area of space, with only a few of the candidates being outliers. They also cluster in distance. That's strange, especially when coupled with the fact that they also cluster in type on the Hertzsprung-Russell diagram. Again, only further work will clarify this, but if the effect is real, then these are among the best SETI targets we have by a long shot. Of course, that does not automatically mean that alien civilizations building megastructures of some type around their stars that looks like dust in one instance would use radio strong enough for us to detect it. But that was another odd mystery with the Tabby Star story. While no radio was detected at Tabby Star, Radio SETI looked. There was a group that looked into potential laser emissions from a group of stars. It was part of a large sample of candidates in a broader search, and they had only one detection. It was Tabby Star. They ultimately concluded it was likely an errant cosmic ray hit on their detector, but strange nonetheless. It would be interesting to see if the new candidates from the two new studies also cluster, and if they overlap with previous studies or each other as far as the candidates go. But one thing is clear. This particular area of SETI is proving to be the most successful as far as candidates, with multiple candidates appearing in each study, whereas Radio SETI only rarely finds individual good candidates that are few and far between, at least for the ones that make it through all of the filtering and procedures. A lot of interesting detections that turn out to be not good candidates we rarely hear about in that part of SETI. But the big question remains, do aliens eventually progress and develop, and are forced to search for greater energy sources? That remains unknown, and can only be answered by an unambiguous detection of an alien megastructure. If we see one, then they do, and we probably will, if we survive long term. But they may not. The vastness of the universe and its realities may simply say that all aliens live within their means, eventually, simply for practical purposes, and stay at home and never turn their star systems into giant energy collectors. But it's worth a look, and in the case of optically detected potential technosignatures, this is one area that's yielding a lot of new candidates to take a further look at. Thanks for listening. I am futurist and science fiction author John Michael Godier, currently wondering why the sun is so angry. I saw an aurora borealis Friday night that made the American Midwest look like Iceland. It was beautiful, but dangerous to power grids and satellites, and really shows what happens when the sun reaches its maximum. And be sure to check out my books at your favorite online book retailer and subscribe to my channels for regular in-depth explorations into the interesting, weird, and unknown aspects of this amazing universe in which we live.